be careful. Don't forget to write it correctly. So this becomes x to the power of negative 17 plus 1 over 3. And obviously that's just x to the power of negative 16 over 3. And final answer is 1 over 3x to the power of 16. Because negative exponents we don't like, so we just switch sides. Now we have a positive exponent. That's the answer for this example there. And here, I'll check to see if I did it right. And you can check the answers there. And, oh wait, here we go. 1 over 3 to the power of 1 over 3 times 6x to the power of 16. And they did it a different way, which is fine. Alright, so close this, close this, close this, close this, close this, close this. Lesson 1, lesson 1 filled. Oh, I highly recommend watching these videos. I would show it right now, but I'm like, you guys can just watch it on your own stuff. The first is a 5-minute video. Highly recommend it. It's a nice overview of what's happening in this new unit. So in this new unit, next lesson when we have it, tomorrow's Saturday, so it's not going to be tomorrow. But whenever the next lesson is, most likely Monday, we'll go over graphing exponential functions a little bit more in detail, but I'm just going to show you just the overview. So, okay, that's terrible, but this is an example of an exponential function. It's a function that kind of starts out slow and then grows rapidly, like shoots up through the sky. So that's called an exponential function. Today, we're not really dealing with graphing exponential functions, so I'm not going to spend too much time on that. I'll just spend it on, I guess, what they want me to expend it on, which is the equation. I mean, the graphs and equations are kind of related, so yeah. But mainly the equation side. So let's take a look at the equation. Oh, first thing I should mention is this. So if you remember from grade 10 and possibly grade 9, first differences. Remember first differences? First differences is when you have a table of values, and then you extend the table of values, and then you subtract the y values, the bottom value from the top value. So in this case, you take 300, subtract it from 100, 900, subtract it from 300, and so on. And then you keep following that pattern, and you see if the first differences are constant or not. If the first differences are constant, that means it's a linear function. It's a line. It's a straight line. And if they're not, well, then you can do second differences, which you just extend the table of values, add another column, and then you subtract the values from the first differences column, and then you have your second differences. And then you see if the second differences are constant or not. And the second differences are the same, meaning constant. They keep, the same number, keep repeating. Then it's a quadratic function. But if it's not constant, then it's neither linear nor quadratic. That's the amount that you've learned so far. Now you're going to learn a new pattern, and that is a pattern not of addition and subtraction, but a pattern of multiplication. Or technical division. Division is the same thing as multiplication, just so you know. Only difference is you're multiplying with the inverse or reciprocal value. So here we're looking for a common ratio. Ratio meaning a multiplicative factor. So you're dividing the second value from the first differences from the top value. So 600 divided by 200, and you'll get a value of 3. 1800 divided by 600, you'll get a value of 3. And then so on. And you keep doing that. You do that for the first differences and second differences, and you realize that the common ratio is 3, and that's an example of an exponential relation or function. An exponential function relation kind of looks like this, starts off slow and then shoots up through the sky. And now we're going to learn this. So this is our general equation when it comes to an exponential growth function. There's two types of exponential functions, technically 4, but we'll get into that later. Exponential growth and exponential decay. So those are the two main ones. The equation is y equals a times b to the power of x. That's your generic equation. And you need to, define what a and b are, and x and y, I guess. So a is your initial amount or population. So the initial value is a. Your b is your growth factor. This is important. This is by how much the exponential relation grows. Y is your future amount or population, and x is the exponent, and that's the number of times a has increased. And this is where students kind of find it a little bit more challenging. Well, x can be a little confusing, but we have a nice little equation for x. To calculate x, use this equation. The total time divided by the time it takes for one growth period. And what does it mean by one growth period? Well, I'm going to give you an example of that now. I don't like this first question. It's annoying. We're going to example 2. Example 2. Let's apply everything that I just talked about. Okay, we got an insect colony, has a current population of 50 insects. Its population is doubling every 3 days. What is the population after 12 days? So, first things first. Always write your exponential equations, especially if it's growth like this. Y equals a times b to the power of x. Now, x is equal to time divided by n. Now, t is equal to time, and n is your growth period. And that is the time it takes for the population, for in this case, it's growing by doubling. So the time it takes for the population to double. How long is the population doubling? It's not doubling every second. It's not doubling every day. It's not doubling every week. It's doubling every 3 days. So my n value in this case is 3. Every 3 days, the population doubles. So we can use common sense here. We can know that, hey, you know what? I'm starting at 50. So that's day 0. So let's say day 0, I'm starting at 50, and then the number population is 50. And then after day 1, 2, 3, I know that after day 3, the population has doubled, so it's going to be 100. So I don't have to actually go up by 1s. I can just go up by 3s. So day 3, the population is 100. Day 6, the population is, remember, it's doubling, so it's going to be 200. Day 9, the population is going to be 400. And day 12, the population is going to be 800. I can just use common sense and be like, hey, you know what? After 12 days, the population should be 800 because I just used common sense, made a table, and just double it up. And that's fine for a small value. And that's a good way to kind of check your answer if you did it right or wrong. But we're going to teach you the equation way because, you know, we usually deal with numbers that are a lot bigger. And, like, you can't really do that. Like, what if I told you 180 days? You're going to make a table of values for that long? I mean, you might, but there's an easier way. What is my A value? Initial population. My A value is 50. So A value is 50, N value is 3. Time, in this case, total time is 12 days, because it's 12 days. And another key important thing that your N and your T have to be the exact same unit. Sometimes in the question, it'll be given where you're doubling every 3 days, but the time is given in like 2 months or something. So you have to convert both of them into days or both of them into months. It doesn't really matter which one. But yeah. Okay, so A is 50. What's my B value? What's my growth? By how much am I growing? I'm doubling, right? So my B value is 2. Doubling. It's going up by 2. Timesing by 2. All right, so now I can write this in my equation. Y is equal to 50 times B, which is 2, to the power of, it's not x anymore. Remember, x is t over n. So you should replace that as t over n. T is the total time, which is 12, and n is your growth period, which is 3. This is my equation. So this is going to be 50 times 2, and 12 divided by 3, that's just 4, 2 to the power of 4. That's 50 times 16, and then that's 800. And that's the answer. Very simple, easy, basic question to start off with.